Okay. Now, in this lecture, we talk about the regular singular points of a differential equation and the related equation known as Euler equation, or sometimes also known as Cauchy-Euler equation. Now, consider again the second order ODE. Consider again the second order linear homogeneous ODE, which is one alternative is to write it in the form P of x y double prime plus Q of x y prime R of x y equal to 0, right? Where P, Q, and R are some analytic functions. Good. Which are analytic at x interval containing x equal to x0. Good. Now, clearly, are some analytic functions in an x interval, let's write that, containing x equal to x0. Clearly, if P of x0 is 0, then x0 becomes a singular point. So we give a classification. Look, when P of x0 is 0, x0 is clearly a singular point. A singular point, let's say SP of the ODE. Okay? Because obviously writing the equation in the standard form, R over P y equal to 0. They are analytic everywhere in some interval containing x0. So these ratios are analytic, but because P of x0 is 0, okay, the coefficients are analytic at any point and not at any open x interval about x0, not containing the point at x0 itself. Good? So x0 is a singular point where the coefficients are clearly undefined. Now we give a classification for these singular points. Okay? Now, here is a definition. Classification of singular points. So with the same assumptions, assume that, or let P of x0 is 0 and x equal to x0 be a singular point of the ODE. Okay? If the limits, look, if the limits, I'm talking about the two limits, look, limit q of x over p of x when x goes to x0. So this limit fails to exist, isn't it? Because p of x0 is 0, so but q of x is analytic. Because we have 0 on the denominator, right? Then, of course, this limit may exist if q of x is also 0. Okay, so 0 over 0, perhaps, which is an indeterminate form, lead to a limit. But in general, when x goes to x0, this limit fails to exist. In any case, q over p is not defined, okay? Even when we have 0 over 0. But look, when this ratio is multiplied by x minus x0, what does it mean p of x is 0? So please be careful. P of x0 is 0 means p of x contains a factor. Okay? X minus x0, or perhaps the square or any power of that, but a positive power. When x is x0, it is 0, contains a factor of this form. Good? A factor like x minus x0. Good? And say perhaps some alpha. Good? So if this singularity at x0 is such that when q over p is multiplied by x minus x0, so this means that p of x contains a single factor, x minus x0 to power 1. If this limit exists, say alpha and not enough, another limit, look at this ratio, r over x over p of x. Now, x minus x0 squared. Okay? So when we consider the second factor, if this limit also exists, okay? If the limits both exist, okay, as finite numbers, so alpha and beta are finite numbers, okay? Then we say that then x0 is called a regular singular point. Say RSP of OD. Use this abbreviation. So we classify the singularity at x0 in this way, looking at these two limits. Good? Otherwise, x0 is classified to be an irregular singular point. Okay? I mean, if one of the two limits fail to exist, okay, at least one or both fail to exist, then the singularity at x0 is called an irregular singularity. Now, we'll see that it is still possible to represent the solution of a second order ODE as a series, but not necessarily a power series, about a point x0, which is a regular singular point. Okay? But we'll see that at least one solution of the ODE. Look, we have a second order ODE, so we expected two independent solutions. And we show that if we expand the solution about an ordinary point, both two solutions are expressible in terms of a power series about x0, where x0 is an ordinary point. Now, we try to extend this idea to find, if there is any, a series representation of a solution of the differential equation about a singular point. First, we give this classification, and we'll see later that actually this is possible whenever x is a regular singular point. Okay? But the series will be of a little bit different type, not a power series. We call it later a Frobenius power series or a Frobenius series. Okay. So look, this definition of singularity, this classification of singular points, implies that, look, if a differential equation of the second order has a regular singularity at x0, it must be of the following form. Okay? Remark. Okay? Alternatively, when x equal to x0 is a regular singular point, of the equation, let's say 1, which is p of x, y double prime, q of x, y prime, r of x, y equal to 0. Okay? It can be written, the ODE may be written as may be written in an alternative form, which is something like that. X minus x0 squared y double prime plus x minus x0 a of x y prime plus b of x y equal to 0. Okay? Where a of x and b of x are both analytic at x equal to x0. Or we may say that Okay. Or more precisely, I should say it is better to say that alternatively, um, if the ODE in by one I consider this form p of x y double prime plus q of x y prime r of x y is this. Can be written as this form, okay, say 2, where a of x, a and b are both analytic at x0, then x equal to x0 is a regular singular point of the ODE. Look, indeed, what I am saying, what is a regular singular point? First, it must be a singular point of the differential equation. So indeed, first, x equal to x0 is a singular point. Of 2, since what? Look at that. We may write it in the form a of x over x minus x0 y prime plus b of x minus x0 squared y equal to 0. And therefore, when we put x equal to x0, clearly the coefficients becomes undefined because a of x and b of x are both analytic under this assumption. So when x is x0, the coefficients becomes undefined, and therefore x equal to x0 is a singular point first. Second, look in this case, okay, compare with this. Suggested by 1, q of x over p of x y prime and r of x over p of x y equal to 0, suggested by 1. Okay? Compare with that. Look, we'll see that this coefficient corresponds to q of x over p of x. And this coefficient in 2 corresponds to r of x over p of x. Good? So if you recall the two limits, now in the new form, with this form, okay? So the two limits, let's do somewhere here. So the two limits, second, furthermore, say, furthermore, the two limits in the classification considered for the classification of the singularity at x0 singularity at x equal to x0 both exist. Look, indeed. Look at that. We require that limit x minus x0 q over x over p of x when x goes to x0 exist. Okay? So if you look at the form in 2, as you see, q over p means that a, so we have this x minus x0, and q over p suggests as a of x over x minus x0. Good. Therefore, this factor cancel each other out, and we have limit a of x when x goes to x0. And this limit exists, say, a of x0. This number exists because a is analytic at x0. So you can think that this is alpha. Okay? So a of x0 exists since a is analytic. And also, the limit in double I we use for the classification of the singular point. This is a classification of the singular point at x0. We require that if the two limits both exist, then we classify the singularity as an irregular singular point. This is the classification. So look, this limit x minus x0 squared rx over p of x implies this x minus x0 squared r of x over p of x is nothing but bx over x minus x0 squared. Therefore, this and this factor cancel each other out, giving limit x goes to x0 of b of x, but b of x is analytic at x0, so bx0. This is b of x0, the value of the analytic function at x0, which may be regarded as beta. So an equation of the form, so clearly, let's remind, an equation of the form an ODE of the form, good, x minus x0, a of x, y prime, and b of x, y equal to 0, has a regular singular point at x0, provided that a of x and b of x are analytic in an open interval containing x0. Okay? So without loss of generality, we may consider a second order equation in this form, if it can be written in that way. Okay? So, and such an equation has a regular singular point at x0. Actually, look, an obvious example of an equation of this structure is the very well-known Cauchy-Euler equation. Okay? Look, an obvious particular case of the equation in 2 is suggested by the so-called Cauchy-Euler equation. So here is the definition. Now, definition, Euler equation, sometimes also called Cauchy-Euler equation. Okay? A particular equation, or ODE, in the form of 2 is this one, x minus x0 squared y double prime plus x minus x0 a y prime plus b y equal to 0. Good. Where a of x is a and b of x is b are both constant functions. Okay? A is a real constant, b is a real constant. So the analytic functions considered in the form 2, okay, are taken particularly as some constant functions. So such an equation are both constant functions is known as, or is called, Euler equation. Good? So clearly x equal to x0 is a regular singular point of the Euler equation. If you take the limits, giving the classification for the singular point at x0, you will see that the limits are a and b. Okay? Look, without loss of generality, in fact, you may define a variable x minus x0, okay? And you can take the singularity at x0, the origin of the x tilde axis. Therefore, without loss of generality, we consider instead x squared y double prime plus ax y prime plus by 0 instead of 3. Oh, let's say this is also 3. Okay? Just use a simple shifting transformation of the independent variable. Okay? So the derivative with respect to x tilde is precisely equal to the derivative with respect to x. So the equation is unaltered in form, but in place of x minus x0, we just write x tilde squared. So the function will be a function of x tilde, but unnecessary to write x tilde. Instead, we take x0, 0 without loss of generality. So this is the Cauchy Euler equation, or simply Euler equation of the second order. Now, with regular singularity, with regular singular point at x0 equal to 0. Okay? Clearly, 0 is a singular point. Consider the reduced form if you want. So a over x, y prime, plus b over x squared y is 0. Okay? Now the condition for the classifications becomes that limit when x goes to 0, because x0 is 0, x times a over x. Okay? This is the coefficient. So which is clearly a. And the second condition for the classification, x squared, x minus x0 squared reduces to x squared b over x squared, which is b. Okay? A and b both exist. So this is an example of a second order ODE where a point stands for a regular singular point. In this case, 0 is a regular singular point of the Euler equation. So also, as you see, Euler equation is an equation with variable coefficients. But, and up to now, we learned that if we deal with a linear equation with variable coefficient, in a general situation, it is impossible, or it is not possible to express all the two linearly independent solutions in terms of elementary functions or finite combination of elementary functions. But this is not the case for the Euler equation. Although the Euler equation is an equation with variable coefficients, we'll see that both two linearly independent solutions are expressible in terms of elementary functions of mathematical analysis, right? This is the importance of the Euler equation. Also, it suggests us a way of looking for series representations of solutions of second order equations about a singular point, which is a regular singular point, but not an ordinary point. Okay? Actually, let's write these remarks. Perhaps the remarks are important. So is it visible? Equation 3 on the screen? Okay. So the Euler equation in 3, okay, has the following properties. So let us give the remarks. First remark is that Euler equation is a linear ODE with variable coefficients. So as I said, in general, we shouldn't expect that both the two solutions are expressible in terms of elementary functions of mathematical analysis. But this is wrong belong for the Euler equation, and we'll present the two solutions in terms of elementary functions later. Second, look, x equal to 0 with variable coefficients, with x0 equal to 0 with a regular singular point at x0 equal to 0. Good. Euler equation in in this form where x0 is taken as 0 with a regular singularity at x0. Second, because x0 is a singular point, okay? General theory or basic theory of linear ODEs suggests that there exist solutions valid either in this interval or in this interval of x, since x equal to x0 equal to 0 is a singular point, although it is a regular singular point. Okay, it is a singular point. Okay, so we find two intervals from 0. These are the largest possible intervals. Okay? Of course, in 0, 1, there exists a solution. Okay, but the largest possible interval is 0, infinity, if we are interested in the positive values, positive real x values, or there is a solution valid in -4, or valid for negative real numbers as well. Okay, this is the case where x is negative. This is the case where x is positive. Okay, so the point at the origin being a singular point, but particularly a regular singular point. Okay, so now to solve the Euler equation, in 3, we may propose, there is an alternative method also, I'm not going to give it. We may propose a solution of the type a solution like x to power r, where r is some constant, real or complex, to be determined. Okay? We are going to propose a solution of this form. Good. To show this, let's write the equation in that form. Okay? So let's consider the operator form. So writing 3, the Euler equation in the form look at that, Ly, that is this x squared d squared dx squared plus ax d dx plus b y equal to 0. Okay? So this is operator L. This is the same equation, Euler equation, okay, written in the operator form. Okay? Now, with the proposed solution in 4, let's write this solution. Proposed solution is this. So what is the idea? If we propose a solution, it must satisfy the equation. So if the proposed solution let's say if x to power r in 4 is a solution, it must satisfy the equation. That is, y of x is x to power r, y prime x is r times x to power r minus 1, y double prime is r minus 1 x to power r minus 2. When we substitute y prime and y double prime into the equation, that is L x to power r, this is y. Good. Here, in place of y, I write this. Therefore, what is that? X squared. Look, x squared y double prime, or let's write that x squared y double prime plus ax y prime plus by equal to 0. So this is Ly. Good. So when you multiply y double prime by x squared, what you get? This becomes r minus 1 x to power r. We multiply y double prime by r squared, x squared, so x to power r minus 2 becomes x to power r. Then multiply y prime by x, multiply y prime by x, so we have a times r multiplying by x, x times r, x to power r, and finally by, so b x to power r. So as you see, every term is proportional to x to power r. The solution, the proposed solution. If it is, I'm not sure. So we get r minus 1 plus ar plus b x to power r. Okay? Or this one, r squared plus a minus 1 r plus b x to power r. Good. Which must be 0. So in other case, in other words, to satisfy the if x to power r is indeed a solution, this must be 0 because x to power r is never 0. Okay, we are looking for a non-trivial solution. This term in braces, this factor in braces must be 0, implying that, so we substitute into the equation, which implies that say 5 r minus 1 a r plus b is 0, or same r squared plus a minus 1 r plus b is 0. Good? So look, this is a second or quadratic equation in R. So we can, in principle, we obtain two roots. This is a second degree polynomial equation. Second degree polynomial equation in R. Okay? So in principle, it has two roots. So corresponding to two roots, we generate a solution of this type. But in the first case, where the two roots are real and distinct, we obviously generate two independent solutions, like x to power r1, x to power r2. But what happens if this equation has a double root? So we get only one r. How can we find the second solution? We'll see that it is possible. And in the case where r may be complex, so x to power r, x is a real variable with an exponent which is a complex number. What is the meaning? Or can we generate real solutions when r is complex? But first of all, we discuss all the three possibilities in this lecture. First of all, this equation for r is known as initial equation, yes, to determine r. So this is a terminology. The quadratic equation in R equation 5 in R is known as the initial equation. Okay. Good. So it is a quadratic equation. So the so-called initial equation, okay, is a quadratic equation. So we have the three cases. So case one, let's consider the three cases that we may encounter. Good. So what is the first case? We have this. So we say that, note that. If r is a root of the initial equation, that is this, r squared plus a minus 1 r plus b equal to 0, then the function x to power r with that R becomes a solution of the Euler equation. Okay?
So equation 5 is called an integral equation, but we know that it's a quadratic equation. So why do we call it special integral equation?
So you mean the origin of this terminology, integral?
Any quadratic equation means integral equation.
No. In connection with the Euler equation, okay, as quadratic equation like that is known as, is called integral equation. Of course, in general, this is just a second order quadratic equation in R. Yes? So when R is the exponent, okay, if the root of the quadratic equation is the exponent of the singularity at 0, okay, this is sometimes called exponent of the singularity, because x equal to 0 is a singular point. In that case, okay, the equation giving R is called integral equation. Okay? Of course, in general, it is a quadratic equation in R. Okay, so we have the following three cases. Case 1. Look, the integral equation is a quadratic equation, and you know that. The so-called discriminant a minus 1 squared, or say when a minus 1 squared minus 4b is strictly positive, the integral equation has two real and distinct roots, say R1, 2, or say R1 and R2, which are distinct, that is R1 and R2, or something like that. Okay, in that case, look at the, we use the formula for the roots of a quadratic equation. So we have minus a minus 1 plus or minus a minus 1 squared minus 4b over 2. Okay? So because this number under square root sign is positive, then square root is positive. So we have the two real roots. Good? When this is the case, we have two solutions. Look, we have two independent or linearly independent solutions, say y1 of x, x2 power r1, and y2 of x, x2 power r2. To have two linearly independent solutions, x2 power r1 and x2 power r2 for the Euler equation. In 3. Okay? Now, here is an example. Consider this equation, x squared or first of all, let's show that these are independent. So if you want to show that they are independent, to show the linear independence, it's enough to consider the Wronski determinant, okay, which is this one, x2 power r1, x2 power r2, r1 x2 power r1 minus 1, r2 x2 power r2 minus 1, okay. Calculating this determinant, what you get, r2 minus r1 x2 power r1 plus r2 minus 1. Good? So clearly, this is not equal to 0. Okay, except when x is 0. When r1 is not equal to r2. Because r1 and r2 are distinct roots. So they are independent. Okay, when x is 0, of course this may be 0, but we know that at x equal to 0 there is a singularity, so it is not surprising that the Wronski determinant is 0 at 0, or maybe 0 at 0, or maybe undefined also. Okay, this is the first case. Here is an example to the first case. Look, let's say, consider this equation, x squared y double prime plus or minus 2x minus 2xy prime plus 2y. Say this. So please be careful. When we identify an equation as an Euler ODE, it is unnecessary to memorize any formula. So this is an Euler ODE. This is an Euler equation. And we propose y of x, x to power r. Okay? Substitution into the equation gives us r minus 1, x2 power r, minus 2 r x2 power r, and 2 x2 power r, or ly, or l x2 power r is this. Good. So we have r squared minus plus r. Good. Oh, this is minus, sorry. So minus 3r plus 2x2 power r is 0. So r squared minus 3r plus 2 is the initial equation, or this one, r minus 1, r minus 2, 0, implying that the two roots of the initial equation are real and distinct. R1 is 1, R2 is 2. Good. Therefore, y1 of x is x, y2 of x is x squared, are linearly independent solutions. Good. So general solution. is of the form y of x, c1x, c2x squared. Now, please be careful. For what values of x is the solution value? Look, this is a nice, x is defined everywhere. X squared is defined everywhere. But we know that Euler equation has a solution which is valid in some interval not containing the singularity at 0. But so this is valid for x positive or x negative. Of course, as a function, it is well defined at the origin. But as the solution of the Euler equation, it is undefined at 0. Look, you can see this if you consider now from the equation, in fact, yes, from Euler equation, under consideration, look, y double prime is written as 2 over x, y prime, minus 2 over x squared y. So at x equal to 0, in fact, y double prime becomes undefined. But a classical solution is a solution which satisfies the equation upon substitution. And it must be differentiable up to second order, at least up to second order. So second derivative fails to exist. Y double prime is undefined at x equal to 0. So given y and y prime independently at 0, look, y double prime will be undefined there. Actually, look, for example, if you think that this solution is valid at 0, then solve this ODE. Solve the initial value problem. Containing minus 2xy prime plus 2y equal to 0. Let's say y of 0 is what? Say 1. Y prime 0 is 0, for example. So from the general solution, y of x, which is when x is 0, so c1x plus c2x squared when x is 0, is always 0, no matter what c1 and c2 are. So, not equal to 1. So, impossible equation. This is not surprising because if you remember the basic theory tells us that if we choose x0, which is in the interval where the coefficient functions are all continuous, then such an initial value problem has a unique solution. However, now 0 is not in the interval where this solution is valid. So this is why I am saying that you shouldn't write that this solution is valid for all r. Yes, if you write that x is r, it seems so. Yes, because x and x squared are well defined for all x, including 0. So for a moment, you can erroneously or incorrectly think that this solution is valid for all x. But if that is the case, then what about this initial value problem? When we pose this initial value problem, we see that we have no solution. Then C1 and C2 remains arbitrary. And perhaps y prime 0 suggests that you determine C2 in terms of C1 and so on, but still there will be infinitely many solutions. So in any case, there will be no unique solution, as suggested by the theory. Okay, there will be a contradiction. But this is not a contradiction with the general theory, because 0 is not in the interval where a solution is sure to exist. So x must be strictly positive or strictly negative. Although this function is well defined as a function, it is well defined at 0, but as a solution of the Euler equation, okay, it is not defined at 0, okay, or it doesn't represent the solution at 0. Okay, so this is the first case where the two roots are real and distinct, two roots of the initial equation, okay, the so-called initial equation, which is nothing but a quadratic equation in R, and R is the exponent of the proposed solution. Now, in a second case, look, case 2, assume that, what was the case 1? Now, look, when a minus 1, this is the discriminant of the initial equation. Here is the initial equation. A minus 1 r plus b equal to 0. Okay? Minus 4b is 0. The initial equation has a double root. That is, R1 is R2. Okay? Explicitly. What is the solution? Minus a minus 1 over 2. Lambda thing. Okay? Is a double root. Okay? Has a double root, R1, R2, good. Discriminant of the quadratic equation, initial equation, discriminant of the initial equation is 0. Then it has two roots, but they are repeated. Say lambda, good. So clearly, y of x, x2 power lambda, or x2 power r, when r is lambda, okay? We propose this solution when r is this number, okay? x2 power lambda is a solution. Say y1. What about the second solution? In this case, good. The equation has two independent solutions. A second order ODE has two independent solutions, valid either for x positive or x negative. But now we find only one solution. Look, in fact, we use this idea again now. If lambda is a root, so note that in this case, the initial equation r plus a minus 1 r plus b equal to 0 may be written as r minus lambda squared. Good. Lambda is this number. Okay? And so r lambda is a double root. And when you write this LXR, what is it? LXR, as we have shown, it becomes r minus lambda squared x2 power r. Okay? So now, clearly, first, x2 power r is the first solution. Obviously, since, look at that, r minus lambda squared, what is required? We require that LXR, we require Lx2 power r is 0. Good. For x2 power r to be a solution. So Lxr is r minus lambda squared x2 power r when r is lambda. Okay? Look, this is 0 because of this factor. And hence, x2 power lambda is the first solution when r is 0. Okay? The equation is satisfied. When r is lambda, this equation becomes indeed 0. So making x2 power r with r lambda, okay, a solution. Good. Or perhaps it is better to write x2 power r when r is lambda. So it is x2 power lambda, okay, is a solution. So what about the second solution? So to find the second solution, we use the idea, what we used it previously in proving the solutions corresponding to an equation with constant coefficient and when the characteristic equation has repeated roots. Okay? So look, you can think that this is an equation. This is a function depending on r and x and taking the derivative with respect to r. So let's say star. So if we differentiate asterisk with respect to r, so we consider that this is a function depending on r and x. So it is a function of two variables with respect to r. Then we have this del r Lxr. That is, look, and if you recall that partial derivative, we can change the order in partial differentiation. Okay? You can write it in this form, L del xr del r. Good. Changing the order. Changing the order of differentiation. Good. So we have to L. So L is the derivative operator with respect to x. Now, so the two operator may be interchanged. So what is the result? Look, I take the derivative of Lxr with respect to r. So I have to take partial derivative of what? Of that. R minus lambda squared x2 power r. Good? With respect to r. So the result is, in this formulation, Look, I'm going to take that derivative. So for simplicity, recall that. Do not forget. Recall that f of x, a function, can be written as e to the power ln of x for f positive. So for a moment, assume x is positive, so x2 power r may be written as e2 power ln x2 power r. Good. And it is written as e2 power r times ln x. Good. And therefore, so with this, now del, let's write again, L del xr del r. So what is that? Del xr del r. And taking the derivative with respect to r. Take the derivative of this with respect to r. We have ln x. Good. I take the derivative with respect to r. So keeping x constant, e to power r ln x. But e to power r ln x is nothing but x to power r. So this is x to power r ln x. Okay? So we have L x to power r ln x. This is the derivative of the left-hand side. And the derivative of the right-hand side. Derivative of the left-hand side. Derivative of the right-hand side, del r. R minus lambda squared xr is what? Take partial derivative with respect to r using product rule. The derivative of the first term is 2r minus lambda, okay, with respect to r times x to power r, and plus r minus lambda squared, derivative of x to power r with respect to r, which is x to power r ln x. Good? Now, when r is lambda, we have, look, lambda is the root of the initial equation. So I see that L x to power r ln x, okay, when r is lambda is 2r minus lambda x to power r plus r minus lambda squared x to power r ln x when r is lambda. So when r is lambda, this is 0, this is 0. So L x to power r ln x when r is lambda is 0, implying that, remember the equation, Ly, okay? So think that this is y. So it satisfies the equation, implying that y x to power r ln x is also a solution. Yes, when r is lambda is also a solution in this case. Good? So when r is lambda, implying that this function, so take it, define it as a second solution because the first solution is x to power lambda. So in this case, y1 of x is x to power lambda, and y2 of x is x to power lambda ln x. Okay? So these are the two cases. So what? Here is an example. Yes, and this is obvious. If we write in this way, we assume that we are interested in positive values of x. So if you are interested in negative values of x, you should choose absolute value of x. Okay? This is for x positive. Okay? So so more generally, you may say that you may write y1 and y2 which is valid for x negative and x positive as well. Okay? So the general solution is the combination, and you can, if you want, you can write down the Wronski determinant to see that the two solutions are independent. Here is an example. X squared y double prime minus x y prime plus y is 0. So propose again y x to power r. So this becomes x squared or r minus 1 multiplying by x squared x to power r minus r, good, plus 1 x to power r is 0, or r squared minus 2r plus 1 x to power r is 0. So individual equation is r minus 1 squared is 0. Good. So r1, 2, r1. Okay? And therefore, y1 of x is clearly x to power r when r is 1. So x, and y2 is x times ln x, or x to power r ln x when r is 1, so x ln x. So again, for x positive, we have the general solution c1x plus c2x ln x. Okay? And finally, if the two roots of the initial equation is a pair of complex numbers, case 3, when a minus 1 squared minus 4b is negative, okay? The initial equation r squared plus a minus 1 r plus b equal to 0 as a pair of complex roots of the form r is lambda plus or minus I mu, where lambda is again minus a minus 1 over 2 as defined in the first case. And what is nu? Nu is the square root of 4b minus a minus 1 squared. Okay? Please be careful. A minus 1 squared minus 4b is negative. So this is positive. So nu is clearly real. Okay? So according to the very well-known formula for the roots of that, okay, we get this solution over 1 over 2. Okay? Do not forget writing 1 over 2. Okay. So in this case, now the function, the complex valued function, x2 power r, when r is this, x2 power lambda plus or minus I mu is a solution. What does it mean? L x2 power r, when r is this complex number, is 0, satisfying the Euler equation. But we are interested in real solutions or real valued solutions of the real variable x. So what is the meaning of this function where the exponent is a complex number? Okay? So again, using very well-known Euler identity, from this identity, Euler identity, which tell us that e to power I theta is cos theta plus minus I sine theta. Good. So we have this. Yx, say, a solution like x2 power lambda plus or minus I mu. So this is x2 power lambda. No problem with this. Real. Lambda is real, x2 power times x2 power plus or minus or plus or I plus or minus mu. Good. Mu is also real. Look at that, defined in this way. So using Euler identity, we have cosine sorry. First of all, let's write the second part. In this case, x2 power lambda, okay? Let's use again this one, x2 power I plus or minus mu, write it as e2 power ln, okay? Plus or minus I plus or minus mu. Okay? What? Ln x, yes. Ln, so what was that? Okay, so we use again the Euler identity, e to power I theta, let's correct this, plus I cos theta plus I sin theta, and y of x, to understand the meaning of this function with a complex exponent, we write it as a product x to power lambda times x to power I plus or minus mu, okay? So we have x to power I plus or minus mu is e to power ln this, or e to power plus or minus I mu ln x. Therefore, we have here e to power plus or minus I mu ln x. So using the Euler identity, we have x to power lambda cosine plus or minus mu ln x, but cosine is an even function, therefore just cosine mu ln x plus sine I times sine plus or minus this, and sine function is an odd function, so we have plus or minus I sine mu ln x. Okay? Is the solution. It is still complex valued, but what is known, we learned that if this complex number is a solution, then its real part and imaginary part are also solutions. So since, recall that, real and imaginary part are also solutions, so recall that if y of x, x to power lambda cosine mu ln x plus or minus I, x to power lambda sin mu ln x is a solution of Ly equal to 0 for, of course, x positive for this case, then real and imaginary parts are both solutions of the same equation. Same ODE, Ly equal to 0. So in this case, two real solutions are given by this x to power lambda cosine mu ln x and y2 of x, x to power lambda sin mu ln x. Okay? For x positive. If you consider a more general solution, which is valid for negative values of x as well, you can take the absolute values of x. Okay? And you may show that the Wronski determinant of the two solutions are not 0, so they are linearly independent.